Hi, this is Tim Atherton. I'm going to be talking today about a collaborative project with Matt Hancock of Penn State University on controlling droplets by surface patterning. The basic idea that Hancock came up with was, as you might imagine, if you put a droplet of water on a surface, it tends to form some part of a sphere. The idea is, what if instead of taking a uniform surface, we take a hydrophobic surface and create a small hydrophilic patch in the surface? If we then pipette some water on it, the water will want to stay within the hydrophilic patch, providing it's not too big, and so we'll create a very complicated, potentially interesting droplet shape. This can be used as a templating technique by dispersing particles into the fluid before we pipette it. These particles, if they're just a little bit denser than water, they'll settle out onto the surface, and if we remove the water, we have a chemical gradient of particles. And clearly, the density of the particles is just going to be proportional to the height of the droplet. The key question that an experimenter might ask is, how do I pattern the surface to achieve a desired deposition profile? And this is what we've been able to help with. So what we're going to take is a known droplet shape for which we know the analytical solution for the height profile, and that's on the top left. And then ask what happens when we modify the boundary. So here we'll put a small notch in the boundary. The boundary is modified by a perturbation zeta, and it turns out that zeta must obey Laplace's equation, subject to the boundary condition that the whole height, the total height, must vanish on the new boundary. Now, because of the simplicity of Laplace's equation, a set of analytical solutions are available from the Schwarz-Christoffel conformal mapping, and what we can do is use this transformation. This transformation maps the long unmodified domain to the modified domain with the notch, as you can see at the bottom. What we can do is solve Laplace's equation in the unmodified domain using a green function, and then simply map the solution back to the domain that we're interested in using the Schwarz-Christoffel mapping. So there's an analytical solution that's quite easy to do. Now, the main results of this analysis are that if we look specifically at the center line of the droplet, which is the bit we're interested in, we can express the profile along the center line essentially as a convolution using this interesting kernel, the hyperbolic secant function. In this way, by relating the problem to a well-studied problem like convolution, we understand why the problem of reconstructing the desired patch shape from a deposition profile is an inverse problem and is a little bit ill-posed. This analysis also allows us to find a maximum achievable gradient. It's shown here. And when we compare this with a numerical solution of the nonlinear equations, the full nonlinear equations, we see that our linearized theory is reasonable. It gives quite good results, as you'll see here in the bottom right, but tends to overestimate the gradients. So that's what I've been up to, and thanks very much for paying attention.